Unit 5, Water and Wastewater. Module 5, Softening and Alkalinity, page 17. The two most common techniques are the lime soda ash method and ion exchange. Water softening removes water hardness caused by the presence of calcium and magnesium bicarbonates and sulfates. Groundwater becomes hard when carbon dioxide in rain percolates through limestone and dissolves small quantities of insoluble calcium carbonate and magnesium carbonate from limestone, producing soluble ions of calcium bicarbonate and magnesium bicarbonate. Small quantities of calcium sulfate are also dissolved from bedrock that contains gypsum, and gypsum is calcium sulfate dihydrate. Calcium bicarbonate and magnesium bicarbonate are referred to as temporary hardness because they can largely be removed, precipitated, simply by heating. So I guess that makes it temporary. So here's soluble calcium bicarbonate, decomposes on heating into solid calcium carbonate, CO2 and water. The precipitation of temporary hardness upon heating is problematic. It deposits scale in pipes, boilers, and even kitchen kettles. Look at the diagrams on the right. Look at the degree of scaling in these pipes and in this heater. Now, scaling in industrial pipes reduces flows and reduces heat transfer, and that's a problem. Sulfate hardness, that is calcium sulfate, is referred to as permanent hardness because it cannot be removed by heating, at least not very much. It's interesting that calcium sulfate has slightly higher solubility in cold water and somewhat decreased solubility in hot water. That's atypical of most salts, but it's only a small difference. Note that magnesium sulfate is highly soluble in water. It's sold as bath salt called Epsom salts. So magnesium sulfate is not a problem unless you boiled the water to dryness, and that's not likely to happen in most industrial settings. Take a look at these equations for the action of lime, calcium hydroxide, on temporary hardness and on permanent hardness. So calcium bicarbonate is temporary hardness. It can be removed by the addition of lime, calcium hydroxide, producing 2 moles of calcium carbonate and water. Magnesium bicarbonate is also temporary hardness and will be precipitated by the addition of calcium hydroxide, producing 1 mole of calcium carbonate, which is solid or insoluble, and 1 mole of magnesium carbonate, also solid or insoluble. Magnesium carbonate is not likely present at any significant concentration in normal water, but if there is some, it'll be precipitated by calcium hydroxide, producing 1 mole of calcium carbonate solid and 1 mole of magnesium hydroxide solid. That takes care of temporary hardness. Permanent hardness is removed by the addition of lime and soda ash together. So magnesium sulfate, if there's any present, will be precipitated by calcium hydroxide, producing magnesium hydroxide solid and calcium sulfate, which has some solubility. But the calcium sulfate is then precipitated by sodium carbonate, producing insoluble calcium carbonate and very soluble aqueous sodium sulfate. So sodium sulfate would not be considered hardness. It will not come out of solution unless you boiled essentially to dryness. So it's not considered hardness. It's very, very soluble. I've listed the solubility of many of these species in the table so you can look at these to prove to yourself that these concentrations of ions can be reduced to very low levels by the appropriate addition of lime and or soda ash. A little extra lime is needed because any CO2 present in water will use up some of the lime, and the CO2 will be precipitated as calcium carbonate. Page 18. So water softening is the reduction of the concentration of calcium and magnesium and a few other ions like ferric ion and aluminum ion. These hardness ions can cause a variety of undesired effects, including interfering with the action of soaps, the buildup of scale in pipes, which can restrict fluid flow and heat transfer as mentioned previously, and even galvanic corrosion. Water softening may be desirable where the source of water is hard. However, keep in mind, hard water conveys some benefits to health by providing a dietary source of calcium and magnesium and reducing the solubility of potentially toxic metals such as lead and copper. Optimal calcium ion removal, that means minimal calcium carbonate solubility, is achieved at a pH of 10 to 10.5. Optimal magnesium removal, meaning minimal magnesium hydroxide solubility, requires a higher pH of about 11. So one of the problems of water softening by lime soda is that it leaves the water with a high pH, 10 to 11, and enough residual calcium carbonate, about 13 ppm, that scale can still slowly deposit over time. So to rectify this, softened water is recarbonated by adding a small amount of CO2 to reduce the pH to a little less than 8.5 or 8.3. See, below 8.3, all carbonates are converted to bicarbonate ion, and the possibility of depositing calcium carbonate is virtually eliminated. If there's no carbonate left, you're not going to precipitate calcium carbonate. Take a look at this graph. So the y-axis shows the fraction of species present versus the pH on the x-axis. An important point on this scale is the fraction of species present at pH 8.3. 100% bicarbonate will be present at pH 8.3. There will be no carbonic acid at that higher pH, and there'll be no carbonate left at that lower pH. If we were to begin with a solution of sodium carbonate and added acid to it, see, this is 100%. This is fraction is 1, that's 100% of carbonate. If we were to begin with that and add hydrochloric acid, it would gradually neutralize the carbonate to bicarbonate. So for example, you can see that at pH 11, the fraction of carbonate present is about 85% here. And at pH 11, the fraction of bicarbonate present, the blue line, is about 15%. So the intersection of the curve with these lines, if you look vertically and add them up, they'll all add to 100%, or a fraction of 1. By the time you reach pH 10.3 or whatever this is, you'll have 50% carbonate, 50% bicarbonate. As we continue to add acid, the carbonate species is gradually being neutralized and more bicarbonate is being formed. So by the time you reach pH 8.3, there's no carbonate left, only 100% bicarbonate. But bicarbonate is a weak base, and it will also be neutralized by the addition of acid. So if we continue adding acid and lowering the pH, the bicarbonate is gradually neutralized and converted to carbonic acid. So for example, at a pH of 6.5, we see we'll have about 65% of bicarbonate and about 35% of carbonic acid, and so on until we reach a pH of about 4. At that point, all bicarbonate has been neutralized and only carbonic acid remains. It's really important that you have an understanding of this for what follows. Carbonate species are so prevalent in lakes and rivers, in boiler water and laboratory water and tap water, that a student really should have a basic understanding of this relationship. In industrial labs, lime soda softened water, that is, being fed to a boiler where scaling must not occur, is titrated with standard sulfuric acid to determine the amount of carbonate and hydroxide that's present, and perhaps bicarbonate. Now the softened water is typically at pH 10 to 11 and is titrated to a phenolphthalein endpoint. Phenolphthalein changes from pink to colorless at pH 8.3, and that measures the amount of carbonates plus any hydroxides. Then bromocresol green indicator is added, and the titration is continued. You do not reserve the burette. You continue the titration down to pH 4, and the color will change from blue to green at 4.5 to 4, and that titrates all of the bicarbonates. Then using the two endpoint teters, one can calculate the amount of hydroxide carbonate and bicarbonate present in the sample. And I present this table because it's in literature sources, but I think it's a waste of time trying to memorize it. Let's just understand what's going on. So we use the symbol P, meaning phenolphthalein endpoint at pH 8.3, where all the hydroxides will be neutralized and all the carbonates converted to bicarbonate. And then we use the symbol B for bromocresol green at pH 4.5 to 4, where all the bicarbonate is titrated to carbonic acid. Some important things you need to keep in mind. First of all, hydroxide and carbonate, they're both bases. They can coexist. Hydroxide is a strong base. Carbonate is a moderately strong base. They can coexist. They can be together in solution. Carbonate and bicarbonate can coexist as well. Carbonate is a moderately strong base. Bicarbonate is a weak base. It's amphoteric. They can coexist, no problem. They don't react with each other. But hydroxide and bicarbonate cannot coexist in the solution. Hydroxide is a strong base. Bicarbonate is amphoteric. It'll react with hydroxide to produce carbonate ion. So hydroxide plus bicarbonate produces carbonate. You cannot have these two species present in solution together. They will not coexist. They'll react. Keep in mind that hydroxide and bicarbonate are both monobasic, whereas carbonate is dibasic. So if I want to neutralize carbonate, it'll require one equivalent of hydrogen to neutralize to bicarbonate, and then another equivalent of hydrogen ion to neutralize bicarbonate to CO2 and water. Take a look at this titration curve to see what's happening. So this is pH on the y-axis, mils of acid on the x-axis. This is a typical titration curve. Titration of carbonates with acid. When you put phenolphthalein indicator in and carbonate is present, the color will be pink because the pH will be higher than 8.3. Let's assume for a minute that only carbonate is present. As one titrates the carbonate to bicarbonate, by pH 8.3 it'll turn colorless. At that point, all of the carbonate has been converted to bicarbonate. Then we add bromocresol green indicator. The solution will turn blue, and we titrate down to a pH of 4 to 4.5 to the green color. By that point, all of the bicarbonate has been converted to carbonic acid. Now, if only carbonate is present, then whatever number of mils it took to bring the color to colorless to pH 8.3, it'll take the same number of mils again to bring the pH from 8.3 down to pH 4 to 4.5. Because every molecule of carbonate produces an equal number of moles of bicarbonate in the titration. If, however, hydroxide is also present, remember hydroxide and carbonate can coexist, then the phenolphthalein endpoint will include all of the hydroxide as well as the carbonate. Now, in case you're wondering about, well, isn't pH 7 neutral? Yes, it is, but the titration curve is so steep in this region for a strong base like sodium hydroxide that you won't even measure a one-drop difference between pH 8 and 7. You essentially will have neutralized 99.9% of all the hydroxide by 8.3. You're not losing anything in accuracy by saying it's all neutralized by 8.3. If both hydroxide and carbonate are present and titrated at pH 8.3, then the titer from 8.3 to 4.5 will be smaller than it was from pH 10 or 11 to 8, because you're only titrating the bicarbonate species, not the hydroxide. Remember that hydroxide and bicarbonate can't coexist. On the other hand, it is possible to have a mixture of carbonate and bicarbonate, and then titration to pH 8.3 neutralizes the carbonate to bicarbonate, and then the titration from 8.3 to 4.5 neutralizes any bicarbonate that was produced from the carbonate plus any bicarbonate that might have already been present, and so the titration between 8.3 and 4.5 can be larger than it was from pH 10 or 11 down to 8.3. So the standard procedure for measuring alkalinity in boiler water is to start with a 100 ml sample of the water. You're going to add phenolphthalein indicator first. and titrate with 0.02 molar HCl or 0.02 normal sulfuric acid. And each mil of acid titer is equivalent to 10 milligrams per liter of calcium carbonate alkalinity. So for example, if the titer of 0.02 molar HCl was 15 mils, then it's 15 mils times 10 milligrams per liter of carbonate alkalinity per mil, so that's 150 milligrams per liter as calcium carbonate. Now this is where it gets tricksy. Hydroxide, bicarbonate, and carbonate have different molar masses, but alkalinity in water samples, regardless of its source of alkalinity, is calculated and reported in milligrams per liter of calcium carbonate. For example, a 100 ml water sample containing only hydroxide might have a titer of 5 mils of 0.02 molar HCl. The alkalinity is reported as 50 milligrams per liter of hydroxide alkalinity. That is 5 mils times 10 milligrams per liter of carbonate alkalinity per mil of acid is 50 milligrams per liter as calcium carbonate. So I have on page 19 5 scenarios. Your job is to report the amount of each alkalinity species present as calcium carbonate. Now, if you first watch the following explanation, you should have a success. The answers are posted on Blackboard. Here's an example that I think will help you understand how alkalinity is reported and why it's reported the way it is. So the molar mass of hydroxide is 17 grams per mole, or 17,000 milligrams per mole. The molar mass of bicarbonate is 61 grams per mole, or 61,000 milligrams per mole. The molar mass of carbonate is 60 grams per mole, or 60,000 milligrams per mole. But since it's dibasic, I can divide that by 2 and say that it has a 30,000 milligrams per equivalent weight. The molar mass of calcium carbonate is 100 grams per mole, or 100,000 milligrams per mole. And since it's dibasic, why not divide by 2 and report 50,000 milligrams per equivalent? Now here I've got 3 different samples of boiler water, 100 mils a sample, titrated with 0.02 normal acid. In sample A, we add phenolphthalein. It requires 8 mils of the acid to bring it to the colorless endpoint at pH 8.3. Then we add our bromocresol green indicator, but it only takes a drop more, essentially no more, just enough to change the color of the indicator, which means there is no alkalinity present between pH 8.3 and 4. So all the alkalinity was present as hydroxide. All hydroxide is titrated by about pH 8.3. So the total alkalinity, using our formula, is 10 milligrams per liter per mil of acid. So that's 80 milligrams per liter. It's all present as hydroxide, but we are reporting it as 80 milligrams per liter as calcium carbonate. Let me show you how that's arrived at. So we have 8 mils of acid, which is 0.008 liters. The normality is 0.2 equivalents per liter or moles per liter, assuming it's monoacidic like HCl. That's 0.0016 moles of hydrogen ion, which neutralized 0.0016 moles of the base, which in this case was all hydroxide, times its molar mass of 17,000 milligrams per mole. Then we want to figure out how many milligrams there were per liter, not per 100 mils, so multiply by a factor of 10. Works out to be 27 milligrams per liter of hydroxide. So that's how much hydroxide is actually present in that sample. But I can report it instead. I'll multiply by the equivalent weight of calcium carbonate instead of that of hydroxide. So I'll multiply the 0.0016 by 50,000 milligrams per equivalent of calcium carbonate times our dilution factor of 10 and report it as 80 milligrams per liter as calcium carbonate. These two numbers represent the same alkalinity. Indeed, they take the same amount of acid. In both cases, they would require 8 mils of the acid. Look at case B. 100 mils a sample, we add phenolphthalein indicator, it's already colorless. We don't have to add any acid to bring it to pH 8.3. That means there's no hydroxide present, nor is there any carbonate present. We add bromocressyl green, and it takes 8 mils to bring it to pH 4 to 4.5. So all that must be bicarbonate ion. The total alkalinity then is 10 milligrams per liter per mil of acid, which is 80 milligrams per liter. But it's all present as bicarbonate this time. But really it's the same amount of alkalinity, isn't it, as the first case? It's just a different kind. Look at the calculation. Again, 8 mils of acid, 0.008 liters, 0.2 moles per liter is the molarity of our acid. 0.0016 moles of hydrogen ion delivered, neutralizing 0.0016 of bicarbonate, times the molar mass of bicarbonate, 61,000 milligrams per mole. What is it per liter? Multiplied by a factor of 10, works out to be 98 milligrams per liter of bicarbonate. But instead of reporting it that way, instead industry chooses to multiply by the equivalent weight of calcium carbonate, 50,000 milligrams per equivalent, times our dilution factor of 10. They report it as 80 milligrams per liter as calcium carbonate, even though it's really 98 milligrams of bicarbonate. And let me argue with you, why can't it be reported as the same amount of alkalinity? It took the same amount of acid, it's present as a different base. Look at solution C. We add phenolphthalein. It takes 4 mils of our acid to bring it to the pH 8.3 endpoint where it goes colorless. We add bromocressyl green. It requires 4 more mils to bring it down to pH 4, 4.5-ish. And so the total mils of acid added was 8 mils. So it has to be all carbonate, because every molecule of carbonate that is neutralized produces an equivalent number of molecules of bicarbonate. That's just the way carbonate neutralizes. You have to go all the way to pH 4 to neutralize all the carbonate, unlike hydroxide, which is a stronger base. So again, 8 times 10 milligrams per liter per mil is 80 milligrams per liter of alkalinity, but this time it's all carbonate. But we report it as calcium carbonate. And here's how we do it. We say 0.008 liters of acid times the molarity, 0.2 moles per liter, means there's 0.0016 moles of hydrogen ion delivered, neutralizing 0.0016 equivalents of carbonate ion, times the equivalent weight of carbonate is 30,000 milligrams per equivalent, times our dilution factor of 10. So actually what's present is 48 milligrams per liter of carbonate, but really it has the same alkalinity as these other ones, so why not report it as calcium carbonate? We're going to multiply instead by 50,000 milligrams per equivalent times 10, 80 milligrams per liter as calcium carbonate. Now we can argue, why shouldn't these be reported as the same number? They are the same amount of alkalinity, they're just present in different forms. So you need to appreciate why this system is in use. In industries that carry out lime soda softening, there's an operator generally in the building that operates the lime soda softening, and then in the boiler room there'll be an operator, and these people take samples and do these titrations probably on an hourly basis. These people have no chemistry training. They don't know the difference between hydroxide, bicarbonate, and carbonate. They simply know that when the alkalinity is 80 or 70 or 60, whatever the number is, they have to respond by adding so many pounds or kilograms of soda ash or lime to the process. Now, using the same system for all three of these different types of alkalinity simplifies the operation. If industry differentiated the type of alkalinity and used different numbers, 27, 98, 48, and whatever, you'd have a much more complicated recipe for the operators to control the process. So this method of operation has been in place in industry for decades. It's simple and it's successful, and that's why it's used. And now you, as a chemical technologist, are in a position to explain to the untrained person what these numbers actually mean. Take a look at this exercise on page 20. Let's suppose you made standard solutions containing the concentrations of various alkalis shown in the table below. Write down the titer of 0.02 molar HCl that would occur at the phenolphthalein endpoint, 8.3, and the bromocressyl green endpoint, 4.5. Sometimes in literature you will see the letter T for total instead of B, and sometimes you'll see M for methyl orange because it's used as well. Then write down the hydroxide, bicarbonate, carbonate alkalinity, and total alkalinity in each case. So going back to our previous example, recall that 100 milliliters of water with 27.2 milligrams per liter of hydroxide in it required 8 mils of 0.02 molar acid to neutralize it. And since it's hydroxide, all 8 mils would be used in bringing the solution to the phenolphthalein endpoint. Because it's a strong base, it would all be neutralized by pH 8.3. Adding bromocressyl green and titrating, well, there'd be nothing else to titrate. There'd be nothing else to add. It would already reach the bromocressyl green endpoint. So the total alkalinity would be 80 milligrams per liter. How do I know? Well, the mils of acid times 10 milligrams per liter per mil. Now we know in this case that all of the alkalinity is present at hydroxide. We would report the alkalinity as 80 milligrams per liter as calcium carbonate, even though it's hydroxide. There's no carbonate and no bicarbonate alkalinity. If you made up a solution that actually contained 97.6 milligrams per liter of bicarbonate, recall that that required 8 mils of 0.02 molar HCl for 100 ml sample. So if you add phenolphthalein, it would already be colorless because bicarbonate doesn't turn phenolphthalein pink. The pH of bicarbonate ion is like 8.3, 8.4. But then in bringing the solution to the bromocressyl green endpoint would require 8 mils to neutralize the bicarbonate. So the total alkalinity again is 8 times 10 milligrams per liter per mil is 80. This time it's all present as bicarbonate. But it's reported as 80 milligrams per liter as calcium carbonate rather than 97.6 milligrams per liter as bicarbonate. Okay, so 48 milligrams per liter of carbonate ion. Let's take 100 mils of that. Recall that that required 8 mils of 0.02 molar acid to neutralize it for a 100 ml sample. So if it's all carbonate, then actually only 4 mils would be required to bring it to the phenolphthalein endpoint where the carbonate is converted to bicarbonate, and then another 4 mils, 4 plus 4 is 8, to the bromocressyl green endpoint. The total alkalinity is 8 times 10 is 80 milligrams per liter as calcium carbonate, but we recognize that all 80 mils are really present as carbonate. What about if we had 27.2 milligrams of hydroxide ion and 48 milligrams of carbonate ion? Well, we know that 27.2 milligrams per liter hydroxide requires 8 mils of acid, and then the 48 milligrams per liter of carbonate required 4 mils to bring it to the phenolphthalein endpoint. 8 plus 4 is 12 mils. Then to get to the bromocressyl green endpoint required another 4 mils of acid for the carbonate that was converted to bicarbonate, and then to titrate that bicarbonate. So 12 plus 4 is 16. The total alkalinity is 16 times 10 or 160 milligrams per liter. And 80 milligrams per liter of that as calcium carbonate was hydroxide, and another 80 of it was carbonate, reported as calcium carbonate, no bicarbonate present. Okay, last case. Let's say we had 48 milligrams per liter of actual carbonate ion in solution, along with 97.6 mils of bicarbonate ion in solution. We took a 100 ml sample and titrated with 0.02 normal acid. What would we find? Recall that bicarbonate is not titrated at the phenolphthalein endpoint, right? It's colorless. But we would be titrating the alkalinity of the carbonate ion. That would be 4 mils for the carbonate. And then from phenolphthalein to bromocressyl green, we'd have another 4 mils for the bicarbonate produced from the carbonate, plus another 8 mils for the bicarbonate itself that'd be 12 more mils, so 4 plus 12 is 16. So again, we're going to have 160 milligrams in total of alkalinity, and of that, none of it is hydroxide. 80 milligrams per liter would be carbonate, and 80 milligrams per liter is bicarbonate, but reported as calcium carbonate. And that's the system that's used in industry. Before we leave this, I wanted to stress, if carbonate is present as the only species, then the BCG titer will be exactly double the phenolphthalein titer, because carbonate is converted exactly into bicarbonate on a molar basis. If the BCG titer is greater than double the phenolphthalein titer, then you must have carbonate plus bicarbonate present. If the BCG titer is less than double the phenolphthalein titer, then you must have hydroxide and carbonate present. Subtract the phenolphthalein titer from the total titer, B titer, to find out how much bicarbonate has been titrated. Where did this bicarbonate come from? If hydroxide was present, then all the bicarbonate must have come from titrating carbonate, because hydroxide and bicarbonate can't coexist. So I know this is something that requires a bit of thought. When I was in the industry, I was faced with the same question by my boss, can you explain to me why this is so? And it took a while, but I figured it out, and you can too if you give it some thought. Do your best with it.